Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers, but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The distinguished lecture series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome.
So, as Man said, that this is a joint session of the Indian Math Consortium Distinguished Lecture Series and IIT Bombay Virtual Computative Algebra Seminar. And our speaker today is very esteemed mathematician, Professor Karen Smith from University of Michigan. And she will speak on extremal singularities in prime characteristic. I want to say a few words. Karen is too well known to most of us, but just for the young people in the audience, I want to say a few words to introduce her to our audience. So Karen is a PhD from University of Michigan, and before she started her graduate studies, she taught even in high school in New Jersey. And it is good that she realized that she could go to graduate school. I don't know how it happened. After finishing her PhD from Michigan under the supervision of Professor Melvin Hochster, she spent a year at Purdue, and she was mentored by Professor Craig Hunicke, who was also one of my teachers when I was at Purdue. She then became a faculty at MIT, spent several years there before she joined University of Michigan in 98, and she is there since then. Karen has received many awards for her very deep work in both algebraic geometry and commutative algebra. In 2016, she became a fellow of the American Math Society, and in 96, which is soon after her PhD, she got the Career Award of the NSF. And in 2001, she won the Ruth Lytle Stater Prize. And I want to read 2-3 lines from the citation just to indicate the breadth of Karen Smith's work. The Ruth Lytle Stater Prize in Mathematics was awarded to her for her outstanding work in commutative algebra, which has established her as a world leader in the study of tight closure, an important tool in the subject introduced by Hochster and Hunicke. It is also awarded for her more recent work, that is before 2001, which builds new bridges between commutative algebra and algebraic geometry via the concept of tight closure. This was in 2001, and in the intervening 20 years, Karen has branched out in many other fields in algebraic geometry and commutative algebra. She is an excellent expositor, and she has actually published two books. Invitation to Algebraic Geometry in 2000 by several other, co-authored with several other people. And in 2004 with Janusz Kolar and Alessio Corti, she wrote the book Rational and Nearly Rational Varieties. And I can see on her homepage more or less completed manuscripts of several other books, including one very interesting book on Frobenius splitting in commutative algebra and algebraic geometry. It is more or less like a book which connects the work of Indian mathematicians, several Indian mathematicians, and American mathematicians about this important topic, which connects all of us. So with these few words, I invite Karen for her talk. And at the end of the talk, we can have question answer session. Thank you very much.
I want to first say thank you very much for the kind invitation and introduction. And you asked me to start my video. So do you want me to start my video? Okay, I can try this. Sorry, I have this background I couldn't figure out how to get rid of. Hi, Graham. I see some old friends out there, which is nice, and new friends like Jyoti Singh, who's one of my co-authors on the paper I'm going to talk about. And I see Trivedi, thank you for coming, and Shinsuke. And I see some new friends. I see my student Shraj Sridhar Pandey is here. So thank you for coming. Let me try to go back to sharing the pictures because I want to talk about these pictures. You don't want to see me. Now it's hard to figure this out. Just a second. Where is my Zoom? Can you see the pictures? No, you don't.
I can see pictures of many surfaces in color.
Oh, they are being shown?
Yes.
Oh, okay. Sorry. I thought
But it's not a video. It's not a video.
Oh, geez, sorry. I had this all set up. I shouldn't have dared to open my camera because now I don't know how to put it back how it was. Just one moment. I should be able. Well, maybe. Am I only in one place? Maybe. Okay, I'm just gonna. Okay, now you see the pictures?
Yeah, we can see.
Okay, so I don't know what's going on. I'll try to do my best here, but okay, so what you see, these are all produced by Herwig Hauser, who's an algebraic geometer in Austria. And all of these pictures are hypersurfaces, and most of them are singular hypersurfaces. So I'm enlarging one. Do you see that one?
Yes, yes, yeah.
The one that I'm enlarging is not singular. Do you notice how it is smooth? There's no points where it pinches itself or crosses itself. Here would be a singular one. Can you see this one?
Yeah.
And this one is another hypersurface. So these are the objects that I'm talking about in this talk. They're hypersurfaces, and I'm interested in understanding the singular points of them. So this green one has a point where it's pinching itself, where it kind of, you can't draw a nice manifold structure there. And there could be much more complicated things. Here you can see, do you see this one where it's crossing itself? These are all made, again, by Herwig Hauser. He has a beautiful website, which probably you can see me linking to here. And this is another example of a hypersurface. It is an algebraic variety, a special kind of algebraic variety. And in this case, we see there are singular points, many of them, because this surface is crossing itself. And every place the surface has a self-intersection is what we would call a singular point of it. Let me try to pull up another one that would be maybe more complicated. Oops, well, maybe, how about this one? Here we can see that there are two lines of singular points where this surface is crossing itself, and then there's an even more singular point in that center where those two lines are crossing and the four bubbles are all pinching together. That is a sort of more singular point than the other singular points. And so what I'm talking about in this talk is trying to understand and quantify those singular points. I'm going to make it precise in a minute, but I wanted to show you some pictures to get started. Does anybody have any questions about that so far what I've got. Can you see it okay?
Yeah, these are surfaces in the Euclidean space or in your characteristic P world.
These are, well, the pictures, of course, are in Euclidean space.
Right.
The pictures are all in Euclidean space. I am going to now share my Jamboard and start making it a little bit more precise what I'm saying. Can you see? You can't see my Jamboard, can you?
Not yet. You can see the picture.
All right, I think it's loading. Start share. How's that? Is it showing now? Now it's showing.
Yeah, now the board is visible.
All right. So, good. Let me now pull up my Jamboard so I can show you precisely what I'm talking about and the results that we proved. So on this page, you can see the title of the paper I'm talking about is Extremal Singularities in Positive Characteristic or Characteristic P. And this is a project with many authors. So I'm not going to list their names every time, but they're right here on the page. We started this project at a workshop in Banff. And I'll also, of course, mention mostly just background for this project, because I understand that this is a colloquium taught for graduate students. But I will tell you the main theorems in that paper. And I'll mention the work of a few other people as I go, including some older work with some older collaborators. But let me try to now make precise what I mean by a hypersurface. So what I mean by hypersurface is I'm going to fix a field. So I'm going to fix a field. So you're really free to think, if you like, about the complex numbers, which is a main case. Although when I get to my theorems, they will be about fields of characteristic P. So for example, you could take just a field of P elements, or you could take, if you like algebraically closed fields, the algebraic closure of that. But really any field for much of the talk will be fine. And what I mean by a hypersurface is this common zero set, or the zero set of some polynomial. So I'm going to consider a polynomial, and I'm going to call it F, and this is in the polynomial ring over that field. So let's say I have n variables, and to focus attention on one point of that polynomial, one point of that hypersurface, I'm going to assume that the polynomial satisfies f of 0 equals 0, so that if I look at the vanishing set of f, so this is the set of all points in Kn such that the polynomial vanishes at that point, this is going to be what we call a hypersurface. So this is what we call a hypersurface. In Kn or in n variables. And because I've assumed that f of 0 is 0, the hypersurface goes through the origin in that space. And my goal in this talk is I really want to try to understand how this hypersurface looks in a neighborhood of that origin point. So in all the examples that I was showing you earlier, there were 3 variables, and all of the hypersurfaces we were looking at were drawn in real R3 space. So the field was the real numbers, the polynomial was in 3 variables, and I didn't tell you the coordinates on those, but we could imagine that we've chosen our coordinates so that one of the singular points we were interested in is the origin. That's kind of the starting point of what I'm doing here. And my goal is really to understand how this question, how can we measure the singularities? How can we measure the singularity at the origin. At a specific point, we want to talk about how singular is the hypersurface there. Can everyone hear me? This is a very strange format to give a talk because I can't see you.
Yeah, you are very clearly audible.
Okay, good. Thank you. Thanks for the thumbs up, Graham. I can only see a couple people's screens, and I appreciate the feedback. This is a really hard way to give a talk. All right, so before we even talk about what singular means, let's talk about what it means smooth, because a singular point is where it's not smooth. So let's remember what it means that it's smooth. So, recall, so this hypersurface V of F, and a lot of times I'll abuse notation or abuse terminology and just say the hypersurface F instead of explicitly mentioning its vanishing set. In algebraic geometry, we tend to conflate the algebra and the geometry. So the algebra is the polynomial, the geometry is its zero set, the geometric object defined by where that polynomial vanishes. So if you hear me say the hypersurface F, you'll know I mean really it's zero set. So the hypersurface is singular, or sorry, let's define smooth first, is smooth at a point P, which I'm assuming is the origin, let's say. What does this mean? This means a couple of things. Intuitively, what it means is there is a well-defined tangent plane. Well, of course, it's going to be a hyperplane at the origin. So for all those pictures I was showing you, if I had a nice smooth one, you could imagine it just locally looking like R2, right? You could draw a nice tangent plane there. For the singular points, you can't do that. More precisely what this means, if you think about how you would do it in calculus, it means that some partial derivative, df dxi, for some I, is not zero at the origin. That would allow us to write out the normal vector to the tangent plane is that gradient, right? If it wasn't zero. Equivalently, another way we could just think about this is if I write my polynomial out, now again, it vanishes at the origin, so there's no constant term. So I have some kind of degree 1 part of it, and then I have some higher order terms. I can write my polynomial out this way. And saying that it's smooth really just says that this is not zero. Not the zero linear form. Because thinking back to calculus, if there was going to be a nice tangent plane there, this would be the defining equation of it, right? This degree 1 part. That would be the tangent plane. It's zero set. And so saying that we are smooth is saying that there's a degree 1 part. And another way we can say this, getting more algebraic again, is that we're saying that F is in the maximal ideal, but not the square of the maximal ideal, where M is this maximal ideal of functions, polynomials that vanish at the origin. In other words, the maximal ideal generated by x1 through xn. Is this clear? Can people hear me? And hopefully this is familiar.
Yes.
Yeah, and in fact, I mean, if you've taught multivariable calculus or maybe taken it recently, you'll recognize that this is, these conditions are basically what's sometimes called the inverse function theorem, if we were over the real numbers. But all of this is how we generalize and think about smoothness when we're talking about a more exotic field, like for example, FP or the algebraic closure of FP. Okay, so keep your eye on this last condition, because this is the one that we're going to move forward with, trying to define what it means that we have a singular point and measure how singular it is. So the most naive thing we could do, the most naive definition or measure of singularity would be what we could call the multiplicity And this is, I'll just define it formally. So the multiplicity of the hypersurface at a point, and again, I'm fixing the origin, is what we're going to do is we're going to look at what power of the maximal ideal am I in. So it is the unique K, let me write this out more neatly, sorry, is the unique K such that F is in M to the K, but not M to the K plus 1. So really, this is just the order of vanishing at the origin. It's the degree of the first non-zero piece of the polynomial, if that makes sense. And notice that F is smooth, or the hypersurface is smooth, is exactly saying that the multiplicity at the origin is 1. So smooth at the origin, right? You could be smooth at one point, but not another one. We're focusing attention on one point. Here, M is, again, that ideal of 0. So the ideal generated by the variables in the polynomial ring. And this is the very first, most naive definition of singularity. So let me just draw a couple of pictures. If I had a singularity that was smooth, and I look at a point here, I can draw a tangent line. Actually, let me not draw that tangent line on the picture because I don't mean to say that that's part of the singularity. I'll do it in a different color. This would be a multiplicity 1 point, if that was my origin. And then a multiplicity 2 point might look like something like this. And then a multiplicity higher, I might have something like this, where I have many crossings. So this is probably multiplicity 2. And this looks like it's at multiplicity large, maybe greater than or equal to 5. However many times I cross there, it's got to be multiplicity at least that. So the multiplicity is our first most naive measure of singularity, but it is not adequate to understand what's really going on. And I'll give you an example. Here are 3 examples. Of multiplicity 2 singularities. So these are going to be multiplicity 2 plane curve singularities. So what I mean when I say plane curve is I'm talking about a polynomial in 2 variables. So I'm looking at the 0 set in the plane. I will get a curve, and I'm interested in the singularity at the origin of that curve. So for example, I could have y squared minus x squared minus x cubed. And this is a nice alpha curve. It has a singular point at the origin. Or I could have a cusp. So that's supposed to be 1. Actually, you can kind of think of it as a degeneration of the previous one, as I sort of look like in the picture. But I have a cusp here. Or I could have a much sharper cusp. And if I have a much sharper cusp, this is going to be more singular. So this first one is barely singular. And what do I mean by that? What I mean is I can actually even see how to resolve the singularities of that, right? If I think of that first alpha-shaped or fish-shaped curve, this first example here, as a piece of wire in the plane, I can imagine just lifting that wire up into 3D. So we call that blowing up, blowing that thing up. And I could see that those 2 different, that crossing will uncross and I'll have a nice smooth curve, right? This is what we would call a normal crossing singularity. So it's in some sense not very singular. And from an algebraic geometry point of view, we often just ignore those singularities. They're very easy to deal with. The second one is more singular because I have a cusp and I can't just simply pick up that piece of wire and uncross it like that. And then this third one, this is more singular, this second example. And this last one is even more singularity, even much more singular. Because this last one, I'm pinched even closer. So if you know about blowing up, you can resolve these singularities by blowing up. And what will happen is you'll need many, many more blow-ups. You'll have to repeat the process of blowing up multiple times and many more times to resolve the sharper cusp than to resolve the less sharp cusp. And what I'd like to do is to come up with some numerical measurement of these singularities. I want to have a numerical measurement of these singularities. So what I'm going to do first is review one that is well known in analysis. And this is called the Log Canonical Threshold. The Log Canonical Threshold, or sometimes the Analytic Index of Singularities. The Log Canonical Threshold sounds like such a terrible jargony name, but it's a pretty simple thing. So this is only going to make sense when we're in a situation like the complex numbers. So let's fix now K to be the complex numbers. So you can also do it for the real numbers or there are ways to do it over other fields. But the way I'm going to explain it, I'm going to assume that the field is C. And I'm going to fix my polynomial F now, and it's a complex polynomial. And again, I'm assuming that it is 0 at 0. And what we're going to do is we're going to look at the function 1 over the norm of F. This is a function, and I'm going to kind of draw a little graph of it. I can think of this as a function from maybe R2n to R, and it's not defined everywhere. Wherever F vanishes, it's not defined, right? It's blowing up. It goes to infinite. It's infinite there. And here, when I say blow up, I mean in the sense of an analyst, I mean it's going to infinity as we're approaching the 0 sets of F, right? As we approach a 0 of F, this is going to infinite. So this is going to be a cartoon of the graph of this function. So the cartoon of the graph, here's my input down here, my R2n. And when I approach a 0 of F, I'm going to have a thing that's blowing up to infinity, right? So this is how it looks. But of course, the inputs are really R2n, and there's going to be a much bigger set where it's going to infinity. And that set is going to be the 0 set of F, where it's going to infinity. But at a singular point of F, what happens is it goes to infinity faster. And so we can talk about where this is integrable or not. And so what I'm going to do, maybe I just define it now. So I'm going to look at the integral in a small ball of radius, let's say epsilon, around the origin. So this is a small ball around the singular point. And I'm going to try to see, when is this square integrable? I'm going to put a lambda here. Oops, sorry, I want to consider the lambdas such that this is integrable. So let's think about what happens if I raise this function to the lambda. If I raise this function to the lambda, I'm going to maybe do it in green. The graph is going to change. If lambda is very small, so the green is a lambda very small, and maybe I'll do, if I have a larger lambda, it would be sort of a wider mouth. Lambda, the yellow is, lambda is larger. And what happens is, I'll shade this in green. If we compute the area under this, it'll converge for some values sufficiently small of lambda. So I can look at sort of the lambda axis here. Oops, I need a different. Sorry, I need an eraser. So if I look at the lambda axis, this is the lambda axis here. I can take a very small lambda and it'll converge, or I could take a very large lambda and it'll diverge. Sorry, this is getting messy. Let me write it neater. So if it's large, the integral diverges. And if lambda is very small, the integral converges, so it's finite. And there's some cutoff point, there's some critical value where when we go past that value, it diverges, and less than that value, it converges. And that's what we call the log canonical threshold. So in other words, it's the supremum over all the lambdas such that this integral converges. So let me state the definition now clearly. The definition, maybe I do it on the next page. No, I'll just write it here. So the definition the log canonical threshold of f at the origin, I'm taking a small ball around the origin to study this convergence, is the supremum over all lambdas such that the integral here I wrote converges in a small ball around the origin. Is this clear, this definition? Can people hear me? I never know if I'm still.
Yes. Yeah.
Sorry. It's so much easier in person when I can see people and I can tell if you can hear me or if you can follow me. I can't tell if I'm being clear or if you can follow me here. So this is one measurement of the singularity. And just to give you an idea of how it does improve the situation over multiplicity, let's look at these three examples that I put earlier. So the log canonical threshold in this barely singular case is always 1. The log canonical threshold in this simple cusp situation is 5, 6. Log canonical threshold in this example, example 2, is 1/2 plus 1/3, which is 5, 6. So slightly less than 1, meaning it's slightly more singular than the barely singular one. And in this much worse singularity, the log canonical threshold is smaller. I need to dampen down that function even more to get the integral converge. And this is 1/2 plus 1/17. I'm not going to add that fraction. You could do that, but the point is it's smaller. We need to damp that function down even more to get convergence of the integral. So this is a much better definition of, or a measurement of singularity. It distinguishes between these three singular points. And it's a very famous singularity. It's used in the minimal model program and birational geometry. You may have heard of it. I am going to write down some properties of it on page 7. I don't have to advance the Jamboard here. You guys can see it on my screen. So properties of the log canonical threshold, let's just list a few. Let's list a few. So it's always positive and it's always less than or equal to 1. So again, this is of a polynomial f at the origin. We always do everything at a point when we're measuring singularities. That's one property. And another property, which is important, is that when f is smooth, at the origin, of course, the log canonical threshold of f at the origin is 1. Now, this is not an if and only if. The barely singular one we talked about earlier, that normal crossing singularity, also had log canonical threshold 1. In fact, the word log canonical can be defined to mean that this threshold is exactly 1. And those are the ones from a birational geometry point of view are as good as smooth things for a lot of purposes. But I'm not going to define log canonical formally, other than that. An interesting property that's not very hard to prove if you have resolution of singularities is that the log canonical threshold is always a rational number. And this follows from resolution of singularities. That's actually a really interesting argument, but I won't do it here, I don't have time. The point is to compute that integral, we can pull back to a resolution of singularities and compute it there. And then it's all very explicitly given in terms of divisors and the Jacobian divisors, the zero sets of where the Jacobian vanishes and so forth of that map. And you can see that it's a rational number. And it's easy to compute in theory if you have a resolution of singularities. Another important property is that how it relates to the multiplicity. So remember, the multiplicity was that order of vanishing at the origin, and this gives us a lower bound. This gives us a lower bound on the log canonical threshold. And what's the important thing from our point of view is that the smaller log canonical threshold means worse singularities. This is how we want to think about this, is a measure. When it's as large as it can be, when it's 1, the singularity is barely singular. And when it's small, and the smaller it gets, the worse that singularity is. That's the idea that we're going for here. Okay, so is that clear? People can still hear me?
Yes. Yeah.
I don't want to just talk into the void. If it's stopped broadcasting, it's kind of embarrassing to keep talking. All right, so this brings us to our question. What about characteristic P? If I'm over the real numbers or the complex numbers, I can integrate, right? Integration makes sense, but it does not make sense in characteristic P. I cannot define, at least I cannot define as I defined it on the previous slide, the log canonical threshold, and I'd like to be able to measure singularities in characteristic P as well. So here, there's work of many people that I think I want to mention without getting into all the details of attributions. But this way of bringing log canonical threshold to characteristic P really goes back to a bunch of Japanese mathematicians who were doing sort of tight closure and related things in characteristic P, including Hara and Yoshida have a paper on this, and Tagaki and Watanabe. And I think these are some of the main names I would want to associate with this, but it all is also all related to the work of Hoekstra and Hunicke in tight closure and characteristic P techniques. And so now I want to define an analog of the log canonical threshold in characteristic P. So what I'm going to do is I'm going to now let fix K to be a characteristic P field. So fix K char P. So again, you can keep in mind a finite field of P elements if you like, or I actually like algebraically closed fields. So maybe we'll think about this example. Then I'm lying less when I'm talking about points and so forth. And let me make a little border here. And again, I'm going to take an F. I'm going to take an F, and that's going to be in the polynomial ring. And I'm going to assume that F vanishes at 0. In other words, F is in the maximal ideal generated by x1 through xn. And in order to make this definition, I need to define one notation. So one notation, I'll do it in green. So one notation is this. M square brackets P to the E is the ideal generated by the P to the E powers of X. Maybe I didn't even need to introduce that notation, but anyway, it's a convenient notation, and it's a familiar one probably to a lot of people who have studied these things. And now I can't integrate anymore But what I can do is I can think about orders of vanishing, because what made that integral blow up of 1 over f was a high order of vanishing at the origin. And so now what I'm going to do is I'm going to look at f, and I'm going to look at when is it in a p to the eth power. Oh, look, I didn't even need the notation because I'm writing this out. And also, when is a power of f in there? So this would be, I want to look at what powers of f are in these. We call this a Frobenius power. Frobenius refers to the pth power map. And I want to look at all of these. Now, what I do is I look at, it's a little hard to motivate exactly why I'm doing this, but I look at all of these fractions, d over p to the e, where f to the d is in the Frobenius p to the eth power of m. And as d gets larger and larger, if I fix the denominator, if I fix p to the e, eventually f to the d will not be in there. Or sorry, it will always be in there, right? And so I want to take the infimum of this. I want to figure out the cutoff point where I get in there, or another way I can put this, maybe it's not completely obvious, but it's a little exercise, that it's also the supremum of when f to the d is not in here. These two numbers are the same. There's a cutoff point where the d to the dth power of f gets in that Frobenius power, and when beyond which it will no longer be. And this is called the f pure threshold. So the definition, the f pure threshold, f pure threshold of f, I'm going to write it this way, fpt of the polynomial f at the origin, everything is specific to that maximal ideal here, right, equals these numbers, these equal numbers, the infimum over all d to the d over p to the e, f to the d is in m p to the e. Okay, now that is a gorgeous definition, not maybe entirely motivated at the moment, but let me give you some of its properties to hopefully motivate it. On the next page, let's write down some properties of the f pure threshold. So first of all, this is a number which is always positive, and it is always less than or equal to 1. Exactly the same as the log canonical threshold. It also has the property that if f is smooth at 0, meaning that the hypersurface is smooth at 0, this will imply that the f pure threshold of f at 0 equals 1, exactly the same as the log canonical threshold. Again, just like the log canonical threshold, this is not if and only if. There are some barely singular singularities in characteristic P as well, and those are called F pure singularities, introduced by Hara and Watanabe, and those are the ones with this F pure threshold is 1. Those are completely analogous to log canonical threshold. And then, just like before, the F pure threshold is always a rational number. Now, this is less obvious, I think. Well, I mean, the log canonical threshold is rational, uses a deep theorem, which is resolution of singularities. But once you know resolution of singularities, that the log canonical threshold is rational is not difficult. This is a theorem of Manuel Blickel, Richard Mastada, and myself. Just want to point out that that's not as easy as the other ones, or as it's not as well known maybe as the log canonical threshold being rational. And now again, the multiplicity gives a lower bound. This is not too hard to see. Again, smaller F pure threshold means more singularity. So to give you an example, I want to point out this thing is really a very perfect analog. It's a much better refinement of the log canonical threshold. So on page 10, here's an example. Let's consider the following cusp, y squared minus x cubed. We already talked about that one over C, right? Over C, if I do a picture, well, of course I'm drawing it over R, but if this one has log canonical threshold equal to 5, 6, we talked about that before. And now what you might imagine is that in you can view that same exact singularity, that same hypersurface, not in C2 or R2, but you could draw it in, or you can imagine it being drawn over a field of characteristic P in K2, where K is characteristic P, and that P could be different for different P. And in fact, as you might imagine, this thing can be more singular in some characteristics than others. So what I want to point out, and this is one of the reasons this is such a great invariant, if I do this in characteristic 2, the F pure threshold is 1/2. If I do this in characteristic 3, it's 2/3. So a little bit closer to 1, not quite as singular in characteristic 3. And now it is 5, 6 minus 1 over 6p. Let me just call it p here. If p is congruent to, p is the characteristic, p is congruent to 2 mod 3, and obviously bigger than 2 since that's a special case. And it is equal to just plain old 5, 6 on the nose if p is congruent to 1 mod 3. So as we see, this is more singular in some characteristics than others. It's most singular in char 2 because this number is smallest, and it's least singular in this characteristic, right? And so this gives us a refinement of the idea that this number can measure the singularities. In complex numbers or in characteristic 0, log canonical threshold is always 5, 6. And notice that if I look at the supremum over all P, over all the F pure thresholds of F over K, as we vary P, as we view of F mod P, right? So I can view this as a character, maybe I'll put F bar. F bar is F mod P. These are approaching the log canonical threshold of F over C. And that's a general theorem. This is due to the mathematicians I listed out, Japanese mathematicians I listed on the previous slide, that the F pure threshold will always essentially, if I think of P going to infinity, approach the log canonical threshold when I have some hypersurface defined over the integers, so that I can view it as being defining a hypersurface over C or defining a hypersurface over any field. So that's a theorem. That's actually a really beautiful theorem of Hara Yoshida and Takagi Watanabe. I think it was stated probably by Takagi Watanabe. But they're also relying on work of the previous mathematicians I mentioned. Okay, so this is supposed to be motivating this point of view that this F pure threshold is an interesting and useful invariant. And that's all background. Now I want to talk about the theorems that we proved with the multi-author paper I mentioned on the very first page. And this has to do with the following question. Now that we have a way to measure singularity, the question is, what is the most singular singularity? Can I define what it means to be the most singular singularity? So if I look at this example, and so y squared minus x to the n, say, what I would see here is we already know that the F pure threshold, or the log canonical threshold, let me call this F, is bounded below by 1/2. That's the multiplicity. 1 over the multiplicity is always a lower bound for both the log canonical threshold and the F pure threshold of F, if I were thinking in a field of characteristic P. And in this case, we can also see that this will, we can approach that, right? The log canonical threshold, this will approach that lower bound. So there is kind of no cutoff point where a singularity is much worse, unless I consider this case, y squared, where the singularity, the log canonical threshold will be exactly 1/2. And that's not a very interesting one, though, because that's not reduced. So this doesn't have a good answer if I think about a general F like that. But to refine this question, I want to make F be homogeneous, so I rule out this phenomenon. So among homogeneous polynomials, F, let's say, of a fixed degree. By the way, if you have a homogeneous polynomial, the degree is the multiplicity. That's the order of vanishing. The lowest degree term that appears is just the degree of the polynomial here. What is the most singular singularity? So is there a lower bound, and maybe I should say better lower bound, right? Better lower bound on the F pure threshold of F, or we could ask this for the log canonical threshold. The answer is not as interesting there. And if so, can we classify, or can we identify the hypersurfaces achieving it? Is it a sharp lower bound, and can we identify, so let me say better and sharp lower bound, that can we identify the hypersurfaces achieving it? There's an argument to be made that those are the most singular possible singularities. If we think of this F pure threshold as measuring the singularities, smaller F pure thresholds means worse singularities. If I've got a lower bound and I've got a hypersurface achieving that lower bound, that is the worst possible singularity. And that's, in fact, exactly our theorem, what we proved. So let me state it on the next page. This is what those authors, co-authors that I mentioned on the front page. It's the following. So I'm going to assume F is characteristic P, sorry, K is characteristic P, algebraically closed. Actually, I don't need that. But K is characteristic P. And F, I'm going to assume is reduced. So by reduced, I mean, if I factor F into its irreducible components, there are no repeated factors, right? And you could just take an irreducible polynomial for this. An irreducible polynomial is automatically reduced. And let's say it's homogeneous of degree D. Again, degree here is multiplicity. Now, we already know that the F pure threshold of F is bounded below by 1 over D. And we know if F is not homogeneous, I can get arbitrarily close to that. But what we proved is actually it's bounded below by 1 over 1 minus d. If I have a homogeneous reduced polynomial, this is a lower bound on the F pure threshold. And this actually kind of a lot of analysis to prove this theorem. And what else we proved, which is interesting, is that this is sharp. And equality holds. We can classify when the equality holds. So equality holds if and only if F has a very special form. So F is x1 to the p to the e. Well, let me write what d has to be. If equality holds, it means that d must be 1 plus p to the e for some e. And F has this very special form. So because of the fact that it's homogeneous and degree d, these LIs are going to be linear forms. And so this is a sort of complete answer to that question. We know that 1 over d minus 1, 1 over the degree minus 1 is a uniform bound for any homogeneous, the F pure threshold of any homogeneous reduced polynomial. And we know exactly that it's sharp and that equality holds only for these polynomials that have this very special form. So we call these extremal singularities. And I don't have time to tell you, but there are many interesting ways in which these singularities are extremal. For one example, let me give you one example. So extremal singularity just means an F that achieves, these are just Fs. These are just Fs that achieve this lower bound. So for one example, just to kind of get a hint in what sense is it extremal, here's an example. If P is characteristic 2, and we look at this equation, this is satisfying. So this is x to the 2, right, times L1 plus x to the 2 times L2, sorry, y to the 2 plus z to the 2 times L3, where L1, L2, and L3 are just x, y, and z respectively. This is the equation. This is a homogeneous equation of an elliptic curve in P2. Now, this is a very special elliptic curve in P2 because this is an extremal singularity. This is a it satisfies that form that we had on the previous page. The log canonical threshold, or the F pure threshold, the F pure threshold of F is a half. So it's not Frobenius split. So this is not a Frobenius split elliptic curve. And what we see about this elliptic, sorry, I don't mean elliptic curve. What am I talking about here? I want to do, sorry. I want to do a cubic surface, not an elliptic curve. Sorry. Everything I said was true, but it's not as interesting as a cubic surface. Cubic surface in P3. One variable up. So this is the homogeneous equation of a cubic surface. So you may remember that cubic surfaces always contain, so they always contain 27 lines, right? There's 27 lines on every cubic surface. Every smooth cubic surface, and this is a smooth one. So the cone over it is not smooth, of course. That's our extremal singularity. But if I look at this, the variety it defines in projective space, that's a smooth cubic surface, and it has 27 lines on it. And what's really special is whenever I have two lines intersecting on it, in general, we would expect the third line. So when I have two lines intersecting, there's always going to be a third line. And in general, it would form like a triangle. But this never happens on an extremal surface. What happens is they always intersect in this more singular configuration of a triangle. We always have a star intersection. So when I take a hyperplane section of an extremal surface, so a surface defined by an extremal equation, one who has maximally bad singularities, what's going to happen is if that hyperplane intersection is a bunch of lines, they all have to intersect in one point, which is a kind of remarkable property, and that's one of the ways in which these things are extremal. So I think I'm out of time. I can tell you that there's a lot more to the paper. We have other ways of thinking about extremalness of these things. And we also have classified up to projective change of coordinates, or up to homogeneous linear change of coordinates, all of them. We can write down a complete classification. There are finitely many isomorphism types, and they're classified by partitions in a really pretty way. So I think I will stop there because I know people have other things to do. Maybe I try to stop the screen share. Is that what I want to do?
Yeah, yes, please.
Figure out how to do that.
Yeah.
Stop share. All right, there we go.
Okay, thank you, Karen, for a very interesting talk. We are open for questions now.
I see there's something in the chat. Is that a question? Oh, somebody said yes. Maybe when I was asking if you could hear me.
Yeah.
Yeah. Can you hear me? I'm Vijay.
Yeah, I can hear you. Mm-hmm.
Yeah, so your question about that F pure threshold tending to log canonical threshold.
Mm-hmm.
So is it F pure threshold is always less than or equal to log canonical threshold for P large?
Yes.
Is it no?
Yeah, yes.
It's always true.
Yes.
And what happens if, what can you say when actually it does coincide for certain P's?
Yeah, that is a very interesting question. Oh, I'm not sharing the screen anymore. Maybe I should share it again. That is a very interesting question, and it's an open question. It's been open for many years. Is my screen not sharing? There it goes. So it's an open question whether there are infinitely many P for which the F pure threshold will equal the log canonical threshold. Let me state it on the board. So let's fix an F with let's say integer coefficients. Of course, you know that we can do this over an arbitrary field. That doesn't really matter, but this is just to make it simpler. And then I can view F mod P as a polynomial in FP. And I can compute its F pure threshold. Or I can view F in the complex numbers, and I can compute its log canonical threshold. And what I was trying to say on the previous slide, it's a theorem of Tagaki and Watanabe that the F pure threshold of F mod P will always be less than or equal to the log canonical threshold, and the supremum of these if I take the supremum over all the different fields, that will always equal the log canonical threshold. And it's an open question. Is the F pure threshold of F mod P equal to the log canonical threshold of f over c for infinitely many p. So we saw in that one example that when p was congruent to 1 mod 3, that we had equality for the cusp, y squared minus x cubed. The f pure threshold and the log canonical threshold agree. They're both 5, 6 for infinitely many p. But they also disagree for infinitely many p, because if p is congruent to 2 mod 3, the f pure threshold is slightly less. It's 5, 6 minus 1 over 6p. But as p gets larger and larger, it converges. It converges to the f pure threshold.
So,
I mean, sorry, to the log canonical threshold.
So this FPT mod P less than equal to LCT, that's for P large, right? Or every P?
Every p, although maybe I need some assumptions about flatness. I mean, I don't want to mod out all the coefficients of f.
And is it some congruence class of P kind of behavior expected for your open question?
No. Here's another example. That used to be expected, but here's another example on page 15. Oh, you don't have to advance. I'm advancing for you. So let's say we take the elliptic curve, like this elliptic curve, and we compute this f pure threshold. So the log canonical threshold of this is always 1. This is a log canonical singularity if I look at it over the complex numbers. But if I look at the corresponding elliptic curve, sometimes it's Frobenius split and sometimes it's not Frobenius split. And here the f pure threshold is 1 minus 1 over p if the corresponding elliptic curve is super singular, which is the same as saying not Frobenius split. And it's 1 if the elliptic curve is ordinary. It is not super singular. So this is saying that it or Frobenius split. I'm just using different terminology. I'm not defining it in case anybody knows either of these. They're equivalent. And I don't believe, by the way, this computation is due to Bargov. It's not very hard, actually. I mean, he has a very hard argument. I have a student who gave a different argument. Anurag Singh also, and Bargov wrote a paper giving another, I mean, a generalization of Bargov's argument. So I don't believe that the super singularity is as simple as just like an equivalence class mod something. Does that answer your question?
Yeah. Okay. Yeah. Thanks. Yeah.
But again, we see that there are infinitely many cases where it's equal to the log canonical threshold. And we also see that as p goes to infinity, it approaches the log canonical threshold. I didn't state it that way on the other page. I just stated supremum. But as p goes to infinity, it does appear that it always approaches. I mean, it's a theorem that it approaches the log canonical threshold.
Yeah. Okay. Thanks. Yeah.
Yeah. This is a very hard open question, whether this is true for infinitely many p, whether the log canonical threshold equals the f pure threshold for infinitely many p. It's been open in one form or another since the late 80s. It's related to the question that came up in the beginning of tight closure theory, whether f pure is equivalent to log canonical or not.
But when it is, so whenever this equality happens, you expect something nice to happen, right?
When the equality happens, we are, yeah, I'm not sure what the question, I mean, it means somehow that the characteristic P singularity you're looking at doesn't have worse singularities because it's characteristic P. It's only as singular as the corresponding complex thing. But I'm not really sure what more I would say than that.
Okay. Okay, thanks, yeah.
Yeah, no worries. Anybody else?
Yeah, there is a question in the chat. Can you see it?
For fixed polynomial f of degree d, what would be LCT for different prime number? And let me see if I understand the question. So we have a homogeneous polynomial. I guess. So and it's degree d. So we know that the F pure threshold of F is always greater than equal to 1 over d minus 1 for all in any characteristic. So I guess you're imagining that F has complex coefficients here and thinking about it in different characteristics. So this is always true. This always holds. And if d is not equal to, e to the e plus 1, then this is strict. But I don't know, and I can't tell you, there's not going to be a simple answer for an arbitrary p, because this is very subtle. It's going to depend very subtly on the polynomial. So for example, if the polynomial was something like x squared y cubed z to the 17 plus, I don't know how to make this, x 5 y to the 13 w to the, I could have some crazy polynomial here. I want to add this, make this homogeneous. So what should that be? 3, 2 plus some u to the whatever number here. This thing, we might expect some weird behavior in characteristics 2, 3, 17, 5, 13. Every single characteristic is going to have its own quirks that are kind of living in mysterious ways in the polynomial, in the coefficients as well. Maybe there's like a 5 here that makes that go away in characteristic 5, makes it much, much more singular in characteristic 5, for example. This is not raised to the 0. I'm just trying to raise it to the number that's going to make this homogeneous. I don't want to do the addition. I guess it's 22. So this should be 4. So, there's no good answer, I think, to that question. It's actually kind of remarkable. That's what I think is kind of remarkable about what we did, is that we have one class of polynomials where we know exactly what the F pure threshold is, and that's actually very unusual. So the examples I showed you of the cusp and of the elliptic curve and then of these extremal singularities, those are almost the only cases where we know a formula for the F pure threshold. There's really no other places where we know formulas. There might be 1 or 2 people have computed and explicit examples, but there's no general formula I can generally give for that. Does anyone else have another question?
Karen, I have a question regarding the lower bound on FPT.
Yeah.
Yeah, so instead of F, suppose you take a complete intersection. Do we know a lower bound?
No, it's a good question.
Nothing is known.
Nothing is known. This is a very new project. We just wrapped it up this fall, and yeah, we have lots of plans to continue, but I have not computed anything in the complete intersection case.
Yeah.
So that's an interesting question. All the students out there should work on it.
Mm-hmm.
And all the old students like me. And you we're all students here, right?
Yes, yes.
So another question, is this theory hold for a variety? Okay, yes, there is a definition of F pure threshold and log canonical threshold for arbitrary subschemes of an arbitrary scheme. Instead of just a scheme of codimension 1 inside of a smooth scheme. And yes, there is a theory there. And so, and most of what I said about the relationship between F pure threshold and log canonical threshold and and the general properties of them hold. However, there's no lower bound that I'm aware of. I mean, I don't think so, because I think I'm the only one that our group's the only one that's been proving lower bounds on these things. We don't know a lower bound any more than what I've stated for hypersurface. So it's a general question to prove lower bounds for these things. Is there another question? I see a lot of people out there, but I don't know if they have any questions. Thank you, Hoghihi. I don't know how to say your name. Thank you for coming.
Yeah.
I don't know how to share my picture. After a year of this, we're still not very good at these remote things, are we?
Yeah.
If there's no more questions, I'll stop
Yeah,
sharing the Jamboard, maybe.
Yeah. I was hoping for a question from Jyoti Singh, your co-author. She is there.
Yeah, she's an important co-author here.
Right.
How do I stop the screen share? Oh, actually, maybe you already did stop it for me. But how do I turn my video on? There we go. Now my video's on. Sorry, I can't figure out how to get rid of this background.
Well, you have to go to these.
I know, I tried. I used to know how to do it, but something went wrong.
Yeah.
So not a big deal.
Yeah. So I guess we don't have questions.
Yeah, Jyoti, I see that she's not connected to the audio, so that could be part of the problem. But so that paper has really two separate halves. One half is proving these lower bounds and studying the sharpness of them, and then understanding the hypersurfaces that achieve the lower bound, that that show that demonstrate or witness the sharpness. But then the whole separate half of it is classifying the ones that are that achieve this lower bound. These, we call them Frobenius forms. And it's a very interesting classification, and it's very similar in a way. It's not really similar, but it's kind of motivated by understanding the classification of quadratic forms, because these Frobenius forms are similar to quadratic forms in various ways. And it's kind of like classifying quadratic forms in characteristic 2.
I see. So
mostly when people classify when people classify quadratic forms, they ignore characteristic 2, right? If you open up a textbook,
right.
An algebra textbook, or you open up a even like pretty advanced research books about quadratic forms, usually the first line is let K be a field of arbitrary characteristic not 2. But you can classify them in characteristic 2 as well. It's actually not that bad. I'm not sure why everybody's so afraid of it, but in characteristic 2, that classification is similar and kind of motivates, and Jyoti was really involved in figuring that out. Why what our classification is similar to the classification of quadratic forms in characteristic 2.
So the property that you mentioned about 3 lines, every bunch of 3 lines meeting only at a point.
Yeah.
That is a characteristic 2 phenomenon.
Well, yeah, it's sort of. If you're talking about a cubic surface.
Okay.
So if we're talking about a cubic surface, it means we have a degree 3 hypersurface, right? Mm-hmm. And the degree 3 hypersurfaces are never going to be extremal unless the characteristic is 2.
I see. Okay.
And so that's the case of extremal cubic surface. An extremal cubic surface is exactly the same thing as a cubic surface where there's no triangles. So whenever you have 3 lines, whenever you have a hyperplane section, which consists of 3 lines, they must meet in a point. Yeah. But that's true for any surface. So if I have any surface defined of any degree defined by a homogeneous polynomial, reduced homogeneous polynomial, and it's going to be extremal if and only if it has this property that every hyperplane section that consists of lines, they all meet in a point.
Mhm.
It's really special. You know, if you have a completely arbitrary surface and you take a hyperplane section, and so that you get lines, right? Most of the time, the lines are going to be some arbitrary line configuration.
Mhm. Mhm.
They're not going to all meet in a point. That's very, very special. And so you see how special these extremal singularities are. In fact, it never happens in characteristic zero. In characteristic zero, when you have a cubic surface, there's always going to be a triangle on it.
Mhm.
And in every characteristic other than 2, there's always going to be a triangle on it. There's always going to be 3 lines that do not intersect in a point.
But in characteristic P, do we have 27 lines again?
Yeah, sure. In characteristic P, you have 27 lines on a smooth cubic surface always, every characteristic.
Okay.
Yeah, the proof of that doesn't use anything about the characteristic of the field.
Mhm. Okay.
Yeah, and if the characteristic is not 2, they may meet in 3 point. You may have triples of lines. They're called tri. You know, you may have hyperplane sections that consist of 3 lines on a cubic surface of characteristic, let's say 5 or 7 or 17, that do meet in 1 point. That can happen, but you cannot have them all meeting at 1 point unless you're an extremal surface, which in this case means characteristic 2, and not only characteristic 2, but that the equation is special, right? The equation has to be x squared times a linear form plus y squared times a linear form plus z squared times a linear form plus w squared times a linear form. And actually, up to change of coordinates, you can always put it into Fermat form, as it turns out.
Yeah.
Not obvious, but it's a fact.
I wonder how the LCT definition in the complex case, using the integral, leads to the FPT definition in characteristic P. How the integral is replaced by FD being in Frobenius power. What is the motivation behind that this is a good replacement?
Yeah, there isn't. Yeah, I mean, you can't directly go from the integral to the. I mean, I can, in hindsight, kind of see why that works, but historically, that's not how it went. It went more that people noticed that this log canonical property was related to F purity, and trying to analyze that connection and coming up with this definition eventually.
Mm-hmm.
But I can kind of a posteriori explain, but it's not very satisfying. It is not a direct, there was no direct connection that goes from the integral to the to this powers being in Frobenius powers proof.
So you think FPT definition is inspired purely by characteristic P considerations, and integral definition has nothing to do with it?
I wouldn't say it has nothing to do with it. It obviously has everything to do with it. I mean, it arose independently. So, Hochster and Hunicke had defined F purity. Sorry, Hochster and Roberts had defined F purity in the 70s with nothing about log canonical anything anywhere in sight. So I think it's just an example that rich objects in mathematics arise in multiple places and have deep connections. And so maybe the way that I presented it made it sound like a posteriori F purity arose in response to log canonical, but it's not true. They both arose independently.
Mm-hmm.
And the fact that you can kind of find a threshold and then compare the thresholds, the F pure threshold was motivated by the fact that people had done this for the log canonical setting. So log canonical as a way to think about singularities, that arose independently of F purity in Mel Hochster's work, and those are just independent of each other essentially. And then people started noticing it's all the same set of examples. they're both useful. They both imply Coleman-Colliness. In one case, it's like the main reason it was introduced. In the other case, I think it might have been proven because of the connection being noticed. But anyway, people prove log canonical implies Coleman-Colli as well. And so, you know, these are two independently arising things that were both out there independently developing by different sets of people. And then for the log canonical world, people were looking at that threshold because there were analysts working on it, and it was natural to like raise something to a fractional exponent and start working with it, right? And so they had this threshold, and then the question becomes, well, how can we put a threshold? How can we do a similar thing in the world of characteristic P? You know, but that's kind of after the fact that the relationship between log canonical and F purity was already there. Actually, Hugo, let me show you the fractional exponent idea, because that's what. Can I share this one more time?
Yes.
How do I do this? Back to Zoom. Share content. All right, so if I now, can you see me sharing? Yeah, you can, but I have to open up Jamboard. So, sorry, it's loading. So what I want to say is that what's cool about characteristic P, and why I think, I mean, this is kind of now meta-mathematical, philosophical, what I think why characteristic P is so closely intertwined with analysis is because it gives us a way to talk about fractional exponents. And sorry, this is still loading. But I'm going to write down that definition of F pure threshold again. And you'll see, this is all a posteriori. Oh, it looks like I might have more questions on here. Do I? No, maybe not. Okay, so let me create another page. Sorry, I should just, all right, so what I'm trying to say is this. Let me write down the definition of F pure threshold. So what we were looking at is F's such that we're looking at F to the D being in M to the P to the E. And then we were looking at the set of all these fractions. And then we were going to take an infimum over them, but just look at that set for a moment. So if I think about this ring, right, the Frobenius gives me a way to identify this ring. Let's assume that K is FP, so I don't have to worry about weird things happening with scalars. But if I can just take this over ring of P to the eth powers, right? This is a bigger ring, but it's of course isomorphic to the original ring, and the Frobenius, the eth power of Frobenius, so every G here just mapping to G to the P to the E. Oh, sorry, that goes in the other direction. So this is an isomorphism. So if I take G and I raise it to the P to the eth power, then I will have an ordinary polynomial in the original ring, right?
Yeah, yes.
And so there's nothing like that in characteristic 0. This is a isomorphism of the ring with itself that's letting me like identify and think about basically taking pth roots of polynomials. So another way I can think about it, if I have an H here, I can take the pth root of it, or the 1 over pth root of it. And this is a perfectly good polynomial. So, you know, I can't do square roots or fractional exponents in general in algebraic geometry or in an algebraic setting, but in characteristic P I can. And so another way that I could think about this statement here is that F is in this fractional power. Let me write this out. That F, I can think of this as saying that F to the D over P to the E is in this fraction, is in this M, right? When I take pth roots of everything, it'll be in here. Now this will be in this ring, not the original ring. But as I said, that ring is isomorphic. Sorry, not D, what in here? So in other words, what I'm looking at is D over P to the E such that F is in, FD over P to the E is in M. So if I think about order of vanishing means like, this is related to like kind of the multiplicity, right? I'm saying that this, this is giving me a way of talking about a fractional power of F blowing up as I approach 0. Being in M is like saying that F of 0 is 0, right?
Yeah.
And so this is like, if I can kind of relate it to blowing up this thing. Blows up in the analytic sense.
Okay.
And so what I'm trying to do is I'm trying to understand, you know, I don't want it to blow up too fast. I want it to be controlled so that I can take the integral. And that's like, you know, looking at when, you know, so if this were not in here, so if this were not in here, that would say that it doesn't blow up, right? So I could take the integral. That would just be a, I mean, it's all philosophical. But if it were not in here, it means this is not going to infinity. And so anyway, I can look at the largest such lambda now, such that that integral makes sense. I mean, there's no integral here, but at least that function is finite. Kind of makes sense?
Yeah.
This is really just philosophical, though. I'm not saying anything that makes sense from a precise point of view.
So by taking the partial, you are just trying to show that it can be continuous and we can perform the integral over it by making it finite, right?
What I'm saying is that if this function is not infinite,
okay,
because it's at 0, because F to the D over P is not vanishing at 0. Because it's not in the maximal ideal. A function being in the maximal ideal is saying that it's 0 at 0. Does that make sense?
Yeah.
This is all just philosophical. There's no actual rigorous mathematics in what I'm saying. And this only makes sense a posteriori, I think. This is not how it was developed. As far as I understand. I mean, maybe, I think Tagaki is here, was here. He might have left. But I think if we asked him, he would say that was not, they were not thinking of integrating these functions at all.
Yeah.
But that is the beauty of Frobenius, is it lets us take roots of functions. And so in analysis, that's what people do as well. They raise functions to small powers to try to dampen them down and integrate them. And we can raise things to fractional exponents in characteristic P. And that's what the beauty of Frobenius is. So I think that's why Frobenius is a good way, why this, you know, that's kind of the secret behind why so many theorems in analysis, or that have been proven using analysis, can also be proven using characteristic P techniques. Such as the Brisson-Skoda theorem, for example.
Right.
That's proven in analysis using integrals, but it's also proven in algebra using this idea of fractional exponents of a polynomial using characteristic P. And again, it's not literally fractional exponents, it's this. You make sense out of it by that, which is intuitively this, or, I mean, you could formally say that as well, but it's not, anyway, that's what I'm saying.
There's a question from Shamik Paul in the chat box.
Yes, the answer is log canonical. So the log canonical threshold is 1 if and only if the singularity is log canonical. And in fact, like I said, log canonical arose first, and then we started putting those exponents on it because it arose in analysis. It's also called the analytic index of singularities, and it had to do with convergence of integrals, like I said, and the characterization of those where, I mean, it really goes the other way, that we first defined log canonicity, and then we defined this threshold as the critical value that we have to raise a function to in order to make it log canonical. So yeah, the answer to the question in the chat is yes, log canonical is the answer.
Okay.
And for F pure threshold, it's exactly the same. The F pure, the singularities for which the F pure threshold is 1 is exactly the F pure singularities. And that's more technical. I don't want to define any of that right now. I mean, I gave a definition. You can use that as a definition.
Okay. I suppose there are no other questions.
Thank you for the opportunity.
Yeah, well, on behalf of everyone, I want to thank you for your very interesting talk and all the philosophical explanations.
Yeah, don't quote me on any of that part of it.
No, it's a good connection. I could not understand why the integral was equivalent to these Frobenius powers, and it starts making some sense now. Yeah,
These are deep theorems. I mean, I mentioned those 4 Japanese mathematicians, and there are many papers. I didn't specifically describe every single paper because these are deep.
Somebody has to know both the worlds. Yeah.
And it's
somebody has to know both the worlds. Yeah.
Sorry.
I mean, I was saying somebody like Watanabe who knows both the worlds could, make the connections and.
Yeah, Watanabe was probably the first person, I think, who really observed that, he was listening to Hochster and Hunicke speak about F purity and F rationality, F regularity, and he was listening in Japan to Mori and whoever else was talking about the minimal model program. And I think in the 80s, he noticed that these are all the same examples that people are talking about. These are all the same interesting things coming up. And he started looking for the connections. And I think he was really the first one who said there might be a connection between F purity and F regularity. Sorry, F purity and log canonicity. But it wasn't just him. There were also, Mel's student Richard Fetter was doing this. And then my thesis later in the early 90s, I did F rationality and some of the connections with rational singularities. And so there's many, many papers underlying all of this that kind of builds toward these numerical invariants being the same. And I only mentioned 4 people.
I recently came to an article. It was stated that if we can treat some kind of prime numbers in the form of binary, then we can convert it into some kind of composite if we just modify the leading zeros over there. So I thought that the thing that you have said recently about all this vanishing criteria, so we can use all those philosophical ideas to implement there as well.
Okay, yeah, I'm not sure I understood that. But if you can use it, that's great. Let me know.
Oh, okay. Yeah.
Yeah, send me the paper you write with it and let me know. Yeah, these are just philosophical ideas. I mean, the fact that the integral is somehow related to this F pure threshold because of fractional exponents.
Yeah.
Thank you.
Okay, Karen. So I think it is time to close. You may have other classes.
I have class at 11.
Yeah.
Linear algebra.
Yeah, we are ending our day and you are starting your day. But still we can meet online, and that's a good point of the pandemic. I hope we will have many more occasions to interact with you online. It is not always.
But not many more pandemics.
No, not many more pandemics. Let things become normal, but we have more opportunities to meet. It takes a lot of effort to cross the 7 seas, but we could meet online with very little effort, and I think there will be some positive effect on interactions. Yeah. So thank
Thank
you.
you for organizing, and thanks to everybody for listening.
Thank you. Thank you. We will close the meeting. Thank you.
Okay, bye-bye.